Imagine this scenario, right? It's 8:30 on a Tuesday morning.
Okay, setting the scene.
Yeah. So a receptionist in your front office is settling in with a coffee, just, sifting through emails.
Pretty standard morning.
Exactly. And one looks like a standard invoice from a vendor they recognize.
Uh.
So they click the attached PDF.
Uh-oh.
Right. Nothing happens. They shrug it off, go back to work. But in the background, a malicious payload just executed.
And the clock starts ticking?
Yep. Within 3 minutes, the attacker extracts a local password hash from that single, low-value workstation. Within 10 minutes, they've used that hash to move laterally across your network, compromising a data center server.
Wow.
And by 9:00 a.m., your entire corporate infrastructure is locked down by ransomware. All because of one clicked link on a receptionist's PC.
It happens so fast.
It really does. Today, we are going to show you exactly how that lateral movement happens and the invisible operational controls that stop it dead in its tracks.
Welcome to the admin study room.
Before we get started, we want to let you know that your hosts today, Jamie and Alex, are AI.
And to set the proper expectations right at the top, we have a quick mandatory note. This is an independent, unofficial MD-102 study podcast based on Microsoft's public Learn content. It is not affiliated with, authorized, sponsored, or approved by Microsoft.
Based on Microsoft's public learning content, here are the topics most worth understanding and reviewing.
Because if you're managing modern endpoints or, architecting security for an enterprise, you already know the stakes.
Absolutely. Securing user identities and enforcing device compliance, they are the absolute bedrock of modern IT.
They really are.
So today, we're building a comprehensive mental model. We aren't going to just list features or read a dashboard to you.
No, that's not helpful.
Right. We are going to connect these concepts into 4 linked layers: strong user authentication, secure organizational access, device trust enforcement, and operational security control.
Which is really the only way to genuinely understand the ecosystem.
Yeah, you have to see the big picture.
Because when people talk about endpoint management, they usually fixate on the flashy, user-facing identity features, right?
Oh, totally. Like biometric sign-ins, passwordless environments.
Self-service portals, all that stuff. And those are critical, but if you stop there, you leave massive blind spots in your architecture.
Because of the underlying operational control.
Exactly. The Intune role-based access, the local administrator password solutions, the literal membership of your local device groups, those are what actually prevent that catastrophic breach scenario you just described.
I really want to spend significant time on those operational controls later, because I feel like they really are the hidden gems of endpoint management.
Well, for sure. They get overlooked all the time.
But we have to build the fortress from the outside in. We can't secure the local administrative rights if the front door is wide open.
Makes sense.
So let's start there. Reimagining identity and authentication. And I guess the core issue we have to solve first is just the password.
The good old password.
Right. We've been told for decades, make them longer, use special characters, change them every 30 days.
Add a number, add a symbol.
Yeah. But the entire concept of a password just seems fundamentally broken for the modern threat landscape.
It is fundamentally broken. And the reason is it relies on symmetric trust.
Symmetric trust. Okay, break that down for me.
Well, a password is a shared secret. You have to know it. And the server you are authenticating to has to know it too.
Right.
And anytime a secret has to be shared or, transmitted over a network or stored in a database, it can be intercepted or stolen. Or extracted.
Because it exists in more than one place.
Exactly. We aren't just dealing with someone guessing a pet's name anymore. We are looking at industrialized credential stuffing.
Let's unpack that term for a second. Credential stuffing. How does that actually work in practice? What is the attacker doing?
So threat actors acquire massive databases of usernames and passwords leaked from other breaches.
Like from completely unrelated websites.
Yeah, maybe a consumer fitness app or some retail website got hacked 5 years ago.
Okay, yeah.
And people reuse passwords all the time. It's just human nature. So the attackers write automated script bots, basically, that take millions of those leaked email and password combinations and simply stuff them into corporate login portals.
Like Microsoft 365.
Right. They just fire thousands of requests a minute. And if even a fraction of a % of your users reused a password from a compromised site, well, the attacker just walked right through your front door.
Without even writing a single line of custom malware.
None at all. Just an automated script.
Man, so the password itself is the liability. Which I guess brings us to Windows Hello for Business.
Yes, exactly.
And I want to be really clear here because I think the marketing terminology can be incredibly confusing for people.
Oh, definitely.
Because if someone buys a consumer laptop off the shelf today at like a big box store, it probably has a fingerprint reader or an infrared camera. And Windows calls that Windows Hello.
Right, the consumer version.
But the enterprise version, Windows Hello for Business, that has entirely different architecture under the hood, right? It's not just a convenience feature for logging in faster.
No, it's not. Consumer Windows Hello is a convenience. Windows Hello for Business is a true passwordless authentication control.
Okay, so what's the core difference?
The distinction is asymmetric cryptography.
So no more shared secret.
Exactly. Instead of a shared secret, we move to a public-private key pair. When a user enrolls their device in Windows Hello for Business, the operating system doesn't just store a picture of their face.
Right, that would be terrible for privacy.
It actually instructs the device's hardware to generate a unique cryptographic key pair.
I'm trying to picture the mechanics of this. If it's a key pair, I'm assuming one part goes to the cloud and one part stays on the laptop.
That's the mechanism, yeah. The public key is sent up to the cloud and registered with Microsoft Entra ID.
Okay.
You can think of it as an open padlock. Anyone can see it, but it doesn't compromise security. The private key, however, never leaves the device.
Okay, but where is it? Does it just sit in a hidden folder on the C drive?
No, that would be vulnerable to malware. It is locked inside a dedicated physical security chip on the motherboard.
The TPM.
Exactly, the Trusted Platform Module, or TPM.
So if I'm understanding this correctly, my fingerprint or my PIN doesn't actually authenticate me to the cloud. My biometric data never goes over the internet.
Never. Your biometric gesture or your PIN acts strictly as a local unlock mechanism.
Okay, wait, so how does the cloud know it's me?
Well, the TPM is like a secure vault. Your face or fingerprint proves to the TPM that you are physically present.
Ah, I see.
The TPM then uses the private key to cryptographically sign an authentication challenge sent down by Entra ID.
And then Entra ID checks the math.
Exactly. Entra ID receives that signed challenge, checks it against the public key it has on file, and if the math checks out, it grants an authentication token.
Wow. That completely changes the threat model.
It really does.
Because if I'm an attacker, and I manage to trick a user into clicking a phishing link, say, one that looks exactly like a Microsoft login page, and the user types in their PIN,
The attacker gets absolutely nothing of value.
nothing at all.
They get a local PN that is utterly useless without the physical device.
Because the private key is stuck in the TPM.
Right. It cannot be extracted from the TPM. It is hardware bound.
Yeah.
The attacker would have to literally steal the physical laptop, know the user's PIN, and bypass whatever conditional access policies you have in place.
Which is a whole lot harder than running a credential stuffing script from another country.
Exactly. It effectively neutralizes remote phishing attacks that rely on stealing credentials.
That is so cool. And it makes total sense for a modern cloud-native organization. But let's look at a hybrid reality.
Yeah, the real world.
Right, because lots of organizations still have massive legacy on-premises Active Directory environments.
Yeah.
They have file servers from 10 years ago, legacy Wi-Fi authentication, maybe older VPN gateways.
Very common.
So if the user is authenticating with a raw public key and Entra ID, how do they access an on-premises domain controller that expects traditional credentials? I noticed the source material mentions two deployment models, key trust and certificate trust. I'm assuming this is where certificate trust comes in.
You're right on track. Key Trust is the cloud-first model we just discussed. It's elegant, and it relies purely on Entra ID handling the public key.
Right.
But legacy on-premises Active Directory Domain Services, ADDS, doesn't natively understand that raw Entra ID key trust for all authentication protocols.
It needs something it recognizes.
Exactly. So for those hybrid environments, we use certificate trust.
So instead of just sending a raw key to the cloud, the device goes to the organization's internal certificate authority.
Yes. During the Windows Hello for Business enrollment process, the device requests a user certificate from the on-premises public key infrastructure, the PKI.
Okay.
That certificate is still bound to the private key protected by the TPM, though.
So the hardware protection is still there.
Yep. And when the user looks at the camera to unlock the machine, the device uses that certificate to authenticate seamlessly to the on-premises domain controller. It typically uses smart card authentication protocols under the hood.
That's fascinating. It effectively turns the laptop itself into a virtual smart card.
That's a perfect way to think about it.
That bridges the gap perfectly for hybrid setups. Even if we implement all of this, the biometrics, the TPMs, the key pairs, we have to acknowledge human reality.
Users will be users.
Exactly. Users will still forget PINs. They will get locked out of devices. They will need to reset credentials.
Which brings up self-service password reset, or SSPR.
A lifesaver for the help desk.
Yeah, from an administrative perspective, this sounds like just a basic help desk offload tool, but it's fundamentally tied into the broader identity security posture, isn't it?
It is, and it's also one of the areas where deployments frequently fail because of a misunderstanding of how the system operates.
Oh, really? How so? Well, SSPR doesn't work by magic. It operates on predefined authentication methods. If a user tries to reset their password, the system has to verify they are who they say they are.
Which means they have to have registered those alternative methods before they forget their password.
That is the critical failure point right there.
They don't set it up in advance.
Exactly. If you turn on SSPR globally, but you don't force your users to register their mobile number, an alternate email, or the Microsoft Authenticator app beforehand, the system is useless when an emergency actually happens.
Because they can't prove who they are, so they're still going to call the help desk.
Yep. Organizations have to run registration campaigns or, better yet, enforce registration at sign-in.
I'd imagine administrators have to be careful about which methods they allow, too. We hear a lot about SIM swapping attacks in the news.
Oh, yeah, huge issue.
Can you explain how that works and why it makes SMS a risky authentication method for SSPR?
Sure. So a SIM swapping attack is essentially a social engineering attack against a telecom provider.
Against the phone company, not the user.
Right. A threat actor calls the victim's cell phone carrier, pretends to be the victim, claims they lost their phone, and asks the carrier to port the phone number to a new SIM card that the attacker controls.
And if the customer service rep falls for it?
The victim's phone just loses service immediately, and the attacker's phone starts receiving all of the victim's text messages and calls.
Including the 6-digit SMS codes for password resets.
Exactly. So if an organization allows SMS as a standalone method for SSPR, an attacker who has swapped the SIM can simply go to the corporate login portal, click Forgot Password,
Receive the code via text on their own phone.
and completely take over the corporate account.
That is terrifyingly easy.
Which is why administrators are increasingly disabling SMS for SSPR and requiring much more secure methods.
Like what?
Like the Microsoft Authenticator app with number matching or FIDO2 security keys. Furthermore, they often require 2 distinct gates.
2 gates, like 2 different methods.
Right. You can't just use one method to reset a password. You must provide a code from your Authenticator app and answer a secure prompt or provide a hardware key.
That makes a lot of sense.
Yeah.
Now let's talk about the hybrid complication again with SSPR.
Okay.
If I am a user whose identity originated in an on-premises Active Directory, and that identity is synced up to the cloud, what happens if I use SSPR in my web browser while sitting at home?
Good question.
Because my password changes in Entra ID, but does my local domain controller in the office basement actually know about it?
Not natively, no.
Uh-oh.
Yeah, if you don't configure the infrastructure correctly, the user will have a new password for their cloud apps, but their old password will still be required to log into their physical workstation when they get back to the office.
Which is going to cause a massive headache and another help desk ticket.
Exactly. To fix this, you must enable a specific feature in the synchronization tool, usually Entra Connect Sync or Entra Cloud Sync.
And what's that feature called?
That feature is called Password Writeback.
Password writeback. Okay, so it takes the cloud password reset and literally writes it back down to the on-premises directory.
In real time. When the user completes the SSPR process in the cloud, the new password hash is securely transmitted back down to the on-premises Active Directory domain services environment.
So the user maintains a unified identity state across both realms? That's smooth.
It's essential for a good user experience.
Okay, so we have secure password resets, and we have Windows Hello for Business replacing passwords on known devices, but we also have to protect access from unknown devices or web portals.
Always.
Which means we have to talk about multi-factor authentication. Now, we've had MFA for years. You type a password, you get a text or an app prompt. But the way we implement it has radically shifted, hasn't it? Why is the old model of just turning on MFA for a user considered problematic now?
The legacy approach is what we call per-user MFA, and it is just a static binary setting.
On or off?
Right. You go into an admin portal, find the user object, and change their MFA status from disabled to enabled. And from that second forward, every single time that user authenticates to a new session, they are prompted for a second factor.
I can see how that creates friction.
A lot of friction.
I mean, if I'm sitting at my desk in a secure corporate office on a trusted corporate network using a corporate-issued laptop, getting prompted for MFA every time I open a new browser tab is going to drive me insane.
It absolutely will, and that friction leads directly to a severe security vulnerability known as MFA fatigue.
Right, where users just stop caring.
Exactly. If you train a user to expect 5 to 10 MFA prompts a day just to do their normal job, they stop looking at the context of the prompts. They just reflexively tap approve on their phone to make the annoyance go away.
Which means if an attacker in another country triggers an MFA prompt using stolen credentials while the user happens to be, say, out to lunch,
The user might just tap approve out of sheer habit.
thinking it's just another annoying system glitch or something.
Yep. And the attacker is in. To solve this, we shift from per-user MFA to conditional access MFA.
Okay, conditional access. How does that change things?
Conditional access is the modern policy engine that evaluates the context of every single sign-in attempt in real time. It doesn't just ask, who is this? It asks, under what conditions is this user trying to authenticate?
So it looks at the broader picture. What kind of signals are we talking about here?
It looks at a lot of things. It looks at the user's group membership. It looks at the application they're trying to access.
Like, is it a low-risk app or a high-risk app?
Exactly. Is it the company cafeteria menu or the high-risk financial database? It also evaluates the network location. Are they coming from a known corporate IP address or some anonymous VPN service?
Oh, that's smart.
It checks the device state, too. Is this a managed, compliant corporate laptop or a personal tablet they just bought?
This allows administrators to be incredibly surgical. You only introduce the friction of an MFA prompt when the context actually dictates it. If I'm on a trusted device, in a trusted location, no prompt, let me work. If I'm on an unmanaged device in a coffee shop, trying to access sensitive HR data, require MFA.
It balances security with productivity perfectly, and it becomes incredibly powerful when you integrate it with Microsoft Entra ID protection.
Identity protection. I want to dig into this because I've always found the terminology here a bit subtle in the documentation.
Can be tricky, yeah.
What is the actual technical difference between a risky sign-in and a risky user in identity protection?
Good question. So a risky sign-in evaluates the specific characteristics of the real-time authentication event.
The event itself.
Right. The classic example is impossible travel. If Entra ID sees a successful primary authentication from an IP address in New York at 10:00 a.m. and then sees another authentication attempt with the same credentials from Tokyo at 10:30 a.m.
The system calculates the geographic distance and the time elapsed.
Exactly. It knows the user couldn't possibly have flown from New York to Tokyo in 30 minutes.
So it flags that specific sign-in event as high risk.
Yep. Other sign-in risks include authenticating from IP addresses known to be associated with malware botnets or from Tor anonymous routing networks.
Okay, so sign-in risk is about the where and how of the current login attempt. What about the risky user?
User risk is a persistent state. It indicates that the identity itself has likely been compromised regardless of the current login attempt.
Okay, how does it know that?
The most common trigger for user risk is leaked credentials. Microsoft's threat intelligence teams constantly monitor public data dumps, hacker forums, and the dark web.
Wow, really?
Yeah. If they find an employee's corporate email address and passwords circulating in a leaked database, identity protection immediately elevates that user's overall risk level to high.
Even if the attacker hasn't actually tried to log in with it yet, the system just knows the password is out there in the wild.
Yes. And this is where the integration with conditional access creates a self-healing security posture.
Self-healing, I love that concept.
It's amazing. Identity protection generates the risk signals, but conditional access enforces the reaction.
Walk me through how that feedback loop works in a real attack scenario.
Okay, let's say a user falls for a phishing scam and enters their password on a fake site. The attacker captures it and eventually tries to log in from an unfamiliar IP address.
Okay.
Identity protection flags the sign-in as medium or high risk. Your conditional access policy sees that risk flag and intercepts the login, stating, because this sign-in is risky, you must pass MFA to prove you are the real user.
And the attacker has the password, but they don't have the user's phone or physical security key, so the attack fails.
Exactly.
But wait, what about the leaked credential scenario? The password is still compromised out there on the dark web.
That's the second layer. If identity protection flags the user risk as high because the credential was found in a dump, a separate conditional access policy can be triggered.
Okay, what does that one do?
The next time the legitimate user tries to log in, even from their normal desk in the corporate office, conditional access will intercept them and say, your account is at risk. Before you can access any applications, you must complete a secure self-service password reset.
That is brilliant. The
Yeah.
system identifies the compromised password on the dark web, flags the user, blocks access, and forces the user to choose a new password, all automatically.
Before the help desk even knows there's an issue,
The threat is neutralized organically.
that is the ultimate goal of modern identity architecture. You move away from static passwords and blanket MFA, and you implement intelligent, context-aware systems that adapt to the threat landscape in real time.
Okay, so we've secured the front door. The identity is verified. The risk is calculated.
Yeah.
But identity is only half the battle.
Yep. It's just the start.
Because if I am the CEO, fully authenticated with a biometric key and zero sign-in risk, but I am attempting to download a sensitive client database onto a malware-infected personal laptop that I haven't patched in 3 years.
That's a problem.
The organization is still facing a massive data breach. The identity is trusted, but the device is not. How do we actually establish device trust?
This is where we transition into device compliance. In an Intune-managed environment, device trust is established through compliance policies.
Compliance policies.
Right. You can think of a compliance policy as the organization's baseline health requirement. It is the rulebook that defines what a device must look like before it is allowed to handle corporate data.
I want to get specific here. What exactly goes into that rulebook? Like, what parameters are we actively checking?
It covers everything from basic configurations to active security posture. The most fundamental check is the operating system version.
Okay, just check in the Windows build.
Yeah, you can set minimum and maximum OS version requirements. If a device is running a build of Windows 10 that reached end of life 2 years ago and is no longer receiving security patches, it is inherently vulnerable.
So the policy simply checks the build number and flags it. What about protecting the physical hardware itself?
We check for device-level encryption. That means verifying that BitLocker is active and securing the volume on Windows devices, or File Vault is active on Mac OS.
Why is that so critical?
It's critical for data loss prevention. Think about it. If an employee leaves their laptop in a coffee shop and someone steals it, they might try to pull the solid-state drive out and plug it into a Linux machine to bypass the Windows login screen.
Oh, right. Just read the drive directly.
Exactly. If the drive isn't encrypted, they can read every single file. If BitLocker is active, the data is just unreadable cryptographic noise without the decryption key.
So we enforce OS versions and encryption. I know mobile devices bring their own unique threats, though. Are we checking for jailbroken or rooted phones?
Absolutely. A compliance policy will actively check if an iOS device has been jailbroken or an Android device has been rooted.
You know, for those who might not know the deep mechanics of it, why is a jailbroken phone such a massive security risk to an enterprise?
Mobile operating systems are built on a concept called sandboxing. Every app operates in its own isolated environment. An app cannot arbitrarily access the memory or files of another app without explicit permission.
So my weather app can't read my emails.
Right. Jailbreaking or rooting is the process of exploiting a vulnerability in the OS to escalate privileges to the root level. Once a device is rooted, that sandboxing is broken.
The walls come down.
Exactly. A malicious flashlight app could theoretically read the memory space of your corporate email app and extract confidential data.
Okay, so a rooted device is a complete non-starter for corporate access. But what about active threats? Can compliance policies integrate with, like antivirus?
Yes, and this is perhaps the most powerful check of all. You can require the Microsoft Defender for Endpoint is active, up to date, and most importantly, reporting a device risk score below a certain threshold.
Device risks.
Right. If Defender detects active malware or suspicious behavioral activity on the endpoint, it elevates the device risk score. The compliance policy sees that elevated risk and immediately marks the device as non-compliant.
I could see a massive trap here for a zealous security administrator, though.
Oh, there are many traps.
Because if I have all these incredible toggles and switches, my instinct would be to configure the policy to be as strict as humanly possible.
Yeah.
Check every box. Require the absolute latest OS patch on day one. Require the highest password complexity. What happens if I deploy a policy like that?
You will likely create an administrative catastrophe.
Really? Why?
Because if you set a compliance policy requiring an OS patch that Microsoft just released 24 hours ago, and you deploy that policy to your entire organization, Your entire fleet will be marked non-compliant simultaneously.
because they haven't had time to download and install the update yet.
Precisely.
And if they're non-compliant, they might lose access to their emails and applications, effectively shutting down the entire company.
You'd essentially be initiating a self-inflicted denial of service attack on your own business, which is why the operational mindset is so important here. You don't just draft a strict policy and push it to production.
You have to test it.
You deploy it to a test group. You review the Intune compliance reports to see how the devices evaluate against the new rules. You give users a grace period to remediate issues.
Like giving them 3 days to install an update.
Exactly, before the policy permanently marks them as non-compliant.
Okay, which brings us to the most crucial conceptual distinction in this entire architectural model. I really want to highlight this because I feel like it is fundamentally misunderstood by a lot of people.
It definitely is.
An Intune compliance policy by itself does absolutely nothing to stop a user from accessing corporate data.
I am so glad you emphasized that.
Right.
A compliance policy does not have enforcement capabilities on its own. It is just an evaluation engine.
It just runs the math.
Right. It takes all the checks we just discussed, encryption, OS version, defender status runs the math, and generates a state. The device is either compliant or non-compliant.
It's just a label.
It is just a label written in the cloud. It doesn't block a network connection or close an application.
It's like an inspector's report. Imagine you are driving a commercial truck. The compliance policy is the mechanic who inspects your brakes, checks your tire tread, makes sure your emissions are in check, and then hands you a piece of paper that says, pass or fail.
Great analogy.
Because that piece of paper sitting on your dashboard does not physically stop the engine from running.
Yeah.
It doesn't physically stop you from driving onto the highway.
It doesn't. To stop the truck, you need someone standing at the entrance to the highway demanding to see the paperwork before they lift the gate.
And that toll booth operator is conditional access.
Exactly. Conditional access is the enforcement mechanism. We discussed earlier how conditional access looks at user risk and location to decide if MFA is needed, while it also pulls in the Intune device compliance state.
Ah, I see how it links up now.
Right. You build a conditional access policy that says if a user tries to access Microsoft 365, require that their device is marked as compliant.
So the user tries to open Outlook. Conditional access intercepts the request. It asks Intune, is this device healthy?
And Intune checks the compliance policy. It sees that the device is, say, missing a critical security patch and replies non-compliant.
Conditional access then drops the toll booth gate and blocks the authentication.
The synergy between the two is what secures the perimeter. Intune measures the health. Conditional access enforces the access based on that measurement.
Okay, let's look at where we are in our mental model. We have robust identity authentication that resists phishing. We have conditional access verifying context. We have compliance policies ensuring the device isn't a malware-ridden liability.
Sounds pretty solid so far.
It is. But now we have a practical networking problem. How does that healthy authenticated device actually reach the data?
The transit layer.
Yeah, because if I'm trying to access Exchange Online or SharePoint, I just go over the open internet. But large enterprises still have vast amounts of data sitting on servers in physical data centers. Legacy ERP systems, custom accounting software, internal file shares.
Stuff that isn't in the cloud yet.
Right.
Yeah.
So if I am sitting in a hotel room in London, how do I securely access a server sitting in a basement in Chicago?
For the last 20 years, the answer has been a legacy VPN client.
The dreaded VPN software.
The user installs an application, types in a server address, enters their password, waits for the tunnel to negotiate, and finally gets an IP address on the internal network. But that model is broken for modern endpoint management.
Because it relies entirely on user interaction.
Exactly. The user has to remember to click connect.
And if they don't, they just don't get access to the files.
Right, but it's worse than that. From an administrative perspective, if the remote laptop isn't connected to the corporate network, it cannot communicate with the on-premises domain controllers.
Which means no updates.
It stops receiving group policy updates. It can't process password changes. It becomes an unmanaged island.
I know Microsoft tried to solve this years ago with a technology called direct access, right? It was supposed to be a seamless, always-on connection. Why did that fall out of favor?
Direct access was revolutionary conceptually, but technically, it was incredibly rigid. It relied heavily on IPv6 transition technologies, which were complex. It required heavy on-premises infrastructure, and it was notoriously difficult to troubleshoot when things went wrong.
So what's the modern replacement?
As organizations shifted toward cloud-managed endpoints and zero-trust architectures, direct access became a legacy anchor. The modern solution that replaces it, and the one heavily emphasized in the current learning material, is always on VPN.
The name is fairly self-explanatory, but how does Always On VPN differ functionally from the old manual VPN clients we used to use?
It is entirely policy-driven and seamless. When deployed correctly via Intune, the VPN profile configures the Windows operating system to establish the encrypted tunnel in the background automatically based on triggers.
So the user never sees a connect button.
Never. They just open their laptop, log in, and their internal applications work.
To really understand how this impacts endpoint management, I think we have to look at the dual tunnel architecture. The documentation breaks this down into two distinct concepts: the user tunnel and the device tunnel. Let's start with the user tunnel. When does that connect and what is its purpose?
The user tunnel connects only after the user successfully authenticates and logs into Windows. It executes in the context of that specific user.
Okay, so it's tied to their session.
Right. Its primary purpose is to provide the user access to the internal applications they need to do their job: web portals, file shares, and client-server applications. It typically authenticates using a user certificate issued by the organization's PKI.
That sounds like a standard VPN, just automated. But the real administrative magic seems to be the device tunnel. If the user tunnel handles the applications, what is the device tunnel doing?
The device tunnel connects at the system level, operating under the context of the local machine account before any user ever logs in.
Before the login screen.
It initiates as soon as the device powers on and detects an internet connection.
Why is that necessary?
Imagine a scenario where an employee goes on a 2-week vacation. While they are gone, their password expires.
Okay.
They return, sit down at their home office, and try to log into their laptop. The laptop says, "Password expired." They call the help desk. The help desk resets the password in the on-premises Active Directory.
But the laptop is sitting at the employee's house. It doesn't know the password was changed because it can't talk to the domain controller to verify it.
Exactly. In a legacy VPN scenario, the user is completely locked out. They would have to physically drive to the corporate office and plug into the network to process the new password.
Which is a huge waste of time.
But with an always-on VPN device tunnel, the laptop established a secure connection to the internal network before the user even touched the keyboard.
Because it turned on as soon as the Wi-Fi connected.
Yep. The device has a clear line of sight to the domain controller. When the user types the new password, the laptop authenticates it against the server immediately.
That is a massive operational lifesaver. It means the IT department can push system patches, deploy software via Configuration Manager, and update security policies at 3:00 a.m. while the laptop is just sitting idle on a kitchen table.
Exactly. It effectively extends the corporate perimeter to wherever the device physically is.
That is the precise value proposition. But as you build these tunnels, you have to make a crucial architectural decision regarding routing. Split tunnel versus full tunnel.
Ah, yes, the great routing debate.
This feels like the classic debate between security visibility and network performance. Walk us through a full tunnel configuration first.
In a full tunnel configuration, the routing table on the endpoint is modified so that every single packet of network traffic leaving the device is forced into the encrypted VPN tunnel.
Every single packet.
Everything. It goes across the internet to the corporate VPN gateway, gets decrypted, routed through the corporate firewall, and then sent to its final destination.
So if a user is sitting at home and decides to stream a 4K video on YouTube during their lunch break, that video traffic goes from Google into the corporate network through the VPN tunnel and back out to the user's house.
Yes, it does. From a security perspective, this gives the organization 100% visibility. Every byte of traffic can be inspected by their intrusion prevention systems and web proxies.
But the performance cost has to be astronomical.
It's terrible. You are backhauling massive amounts of non-corporate internet traffic, exhausting your VPN gateway bandwidth, and creating terrible latency for the user.
Which is why the industry has largely shifted to split tunneling. How does that change the routing?
A split tunnel uses precise routing rules. Only traffic destined for specific internal corporate IP subnets is routed through the VPN tunnel.
So it splits the traffic based on destination.
Right. If the user tries to access the internal HR server, it goes through the tunnel. If the user tries to access YouTube or even cloud-based corporate apps like Microsoft 365, that traffic goes straight out their local home internet connection.
The performance is vastly improved, and you aren't paying for the bandwidth of 1,000 employees streaming music.
Exactly.
But wait, What happens to the security visibility? If the traffic isn't passing through the corporate firewall anymore, how do you protect the device from malicious websites?
You have to push the security controls down to the endpoint itself. You can no longer rely on a centralized firewall choke point.
So we're back to Defender.
Exactly. This is where tools like Microsoft Defender for Endpoint come in. Defender runs locally on the machine, inspecting web traffic, blocking malicious domains, and providing web content filtering regardless of whether the traffic goes through the VPN or the local internet.
So split tunneling is the preferred modern architecture, provided you have robust endpoint security compensating for the lack of network-level inspection.
That's the trade-off, yes.
There is one more elegant feature of Always-On VPN that I want to explore. Trusted network detection.
It's a great feature.
Because if I'm an employee and I take my laptop from my home office and commute into the corporate headquarters and I plug into the Ethernet at my desk, my laptop is now sitting physically inside the corporate network. I don't want it trying to build a VPN tunnel to the server sitting 50 feet away.
And it won't. Trusted network detection acts as a geographic awareness toggle. When configuring the VPN profile in Intune, administrators specify a specific internal DNS suffix,
like internal.corp.com or something.
Right. When the device connects to any network, it silently queries for that DNS suffix. If the query resolves, the device knows, I have direct line of sight to the internal network. I am inside the perimeter. It immediately pauses the VPN connection.
And when I unplug and walk to a coffee shop down the street, it runs the query, fails to find the internal DNS, realizes it is outside the perimeter, and automatically spins the tunnel back up.
It's completely transparent to the user.
That is so smart.
It is, when it works. But this brings up a critical troubleshooting reality.
Uh-oh. Troubleshooting reality. Lay it on me.
If you are an administrator and you configure an always-on VPN profile in Intune and deploy it to a group of devices, the Intune portal might report 100% success.
Okay.
But your users are calling saying the VPN isn't connecting.
Wait, how is that possible? If Intune says the deployment was successful, shouldn't it be working?
Intune's definition of success is simply that the configuration profile, the XML file containing the settings, was successfully delivered to the Windows registry.
Oh.
It does not mean the infrastructure is capable of supporting the connection. Always-on VPN has massive external dependencies.
Like what?
Well, if the VPN relies on certificates for authentication, and the device failed to request a certificate from the internal certificate authority because a server was down, the tunnel will fail to build.
Or if the external DNS record for the VPN gateway is pointing to the wrong public IP address. The client has the instructions, but it's basically calling a dead number.
Exactly. Intune configures the client. It is up to the architect to ensure the broader network, PKI, and identity infrastructure are fully operational.
Okay, let's step back and look at our fortress. We have strong identity, we have device compliance checking health, we have always on VPN securing the network transit.
It's looking pretty good.
But there's the glaring vulnerability we haven't addressed yet. What happens if an attacker bypasses the network entirely? What if they get physical access to a device, or they manage to execute a localized script on the endpoint? If they can escalate privileges locally, all of our cloud-based conditional access policies are irrelevant.
We need to look under the hood.
Let's talk about operational control and local privileges.
This is an area heavily emphasized in Microsoft's security documentation, and for good reason. Mismanaged local administrative privileges are the primary vector for widespread ransomware deployments.
Let's start at the top, with the privileges inside Intune itself. We discussed earlier how assigning a compliance policy that is too strict can cause chaos. The same principle applies to admin access. A security design fundamentally fails if too many administrators have unrestricted power.
This is the principle of least privilege. When an organization adopts Intune, the path of least resistance is often to assign every member of the IT department the global administrator, or Intune administrator role in Entra ID.
Just to make things easy.
Right. It prevents them from ever seeing an access denied error when trying to do their job.
But it also means a junior help desk technician has the power to accidentally wipe every single CEO and executive laptop simultaneously.
Or even worse, a compromised help desk account can be used by an attacker to deploy malware as an application payload to the entire organization.
Broad tenant-wide permissions violate least privilege.
Intune provides role-based access control, or RBAC, to solve this.
Let's run a scenario to make this concrete. We have a regional IT administrator based in Berlin. Their sole responsibility is managing the hardware, compliance, and application deployments for the 500 employees located in the German offices. How do we restrict their access so they can't impact the office in New York?
We use a combination of custom roles and scope tags.
Okay, what's the difference?
First, we create a custom role that defines what they can do. Perhaps they have permission to create compliance policies, deploy apps, and remote wipe devices. Then, we apply a scope tag to that role to define where they can do it.
So we tag all the devices in the German offices with a specific Berlin tag.
Yep. When we assign the role to the regional admin, we link it to that scope.
So when the Berlin admin logs into the Intune portal, they don't even see the devices from New York. They can only execute actions against the assets tagged for their region. It effectively isolates the administrative blast radius.
Exactly. The key takeaway for anyone studying this architecture is that the technically expedient action like assigning global admin to make a problem go away is almost always the wrong architectural decision. You must always seek the most restrictive path that still enables the business function.
That locks down our cloud administration.
Right.
But what about the physical hardware itself? Every Windows machine has a built-in local administrator account.
Yes, it does.
Historically, the standard operating procedure for IT departments was to build a master image, set the local administrator password to a standard string like support 2024, and then clone that image to 5,000 machines.
Which is an absolute nightmare for security. It introduces a critical vulnerability known as lateral movement.
We mentioned lateral movement in our very first scenario with the receptionist. I want to break down the anatomy of that attack. What does lateral movement actually look like at a technical level?
Let's trace it step by step. A threat actor compromises a single low-value endpoint, say, that receptionist's PC, via a phishing payload. The attacker establishes a foothold on that machine. They now have local access. Now, the Windows operating system stores the hashes of recently logged on users, including local administrators, in a memory process called LSAS.
LSAS. What does that stand for?
The Local Security Authority Subsystem Service.
So the attacker runs a credential dumping tool, like Mimikatz, to scrape that memory process.
Yes. They extract the password hash for the built-in local administrator account. And if the IT department used a static, cloned password across the entire environment, that hash is identical on every single machine in the company.
The attacker doesn't even need to crack the hash to figure out the password is support 2024.
Right.
They can just use a technique called pass the hash.
Exactly. They take that extracted cryptographic hash and simply present it to another machine on the network, perhaps a database server or a domain controller.
And because the destination machine shares the exact same local admin password, it accepts the hash as valid authentication.
The attacker moves laterally from machine to machine, escalating their access without ever needing to exploit another vulnerability or crack a single password. One compromised receptionist PC instantly compromises the entire fleet.
That is terrifying. The entire network falls like dominoes just because they all share the same master key.
Yeah.
How does a modern endpoint architecture stop this?
We implement Windows LAPS, the Local Administrator Password Solution.
LAPS.
LAPS natively integrates with Entra ID and Intune. It fundamentally breaks the lateral movement chain by automating the management of that built-in local administrator account.
How does it manage it? Like, what does it actually do?
When LAPS is deployed via Intune, it instructs the endpoint to generate a completely unique, randomly generated complex password for the local admin account. It then securely transmits that password up to Entra ID, where it is stored in the device's object properties.
So instead of 5,000 machines sharing one password, we have 5,000 machines with 5,000 completely different random passwords. If the attacker compromises the receptionist's PC and scrapes the LSAS memory now, what do they get?
They get a password hash that is only valid for that specific receptionist's PC. If they try to pass that hash to a server, the server will reject it because the server has its own unique password.
The lateral movement is stopped dead. The compromise is successfully isolated to a single machine.
It's a huge win for security.
But wait, IT still needs to fix things. If a device drops off the network and a field technician needs to log in locally to fix a corrupted network driver, how do they get the password if it's random?
Authorized administrators can log into the Untra or Intune portal, look up that specific device, and click a button to reveal the current LAPS password.
Oh, nice.
Furthermore, LAPS is configured to rotate these passwords dynamically. You can set a policy that says rotate the password every 30 days, or rotate the password immediately after it has been retrieved by an administrator.
This ensures the password is never viable for long-term exploitation.
Exactly. LAPS is a brilliant solution for the built-in account. But there is another layer to local privileges, and this is an area where I see constant confusion.
Oh.
LAPS handles the master admin account, but Windows also has a local administrators group. Intune provides a feature to manage local group membership. Why do we need to manage the group if we already randomize the master password with LAPS?
That's a good question.
Because the built-in account is just one door.
Yeah.
The local administrators group is a container. Any user account that is placed inside that local group is granted full administrative control over the machine.
So the security vulnerability we're addressing here is not lateral movement.
No, it is privilege drift.
Privilege drift, I like that term. It implies a slow degradation of security over time.
It's the reality of IT operations. Let's say a developer submits a ticket stating they need temporary local admin rights to install a legacy compiler that requires deep system access.
Very common request.
Right. A help desk technician manually adds the developer's Entra ID account to the local administrators group on their laptop. The developer installs the software, the ticket is closed, and everyone moves on.
But the technician never went back and removed the account.
Exactly. 3 years later, that developer is still browsing the internet, opening emails, and executing downloaded files with full, unrestricted system privileges.
And if they accidentally execute malware?
The malware runs with local admin rights and can embed itself deeply into the OS, disable the antivirus, and steal data.
It's a massive risk. So how does Intune local group membership management solve this?
It allows administrators to define the exact desired state of those local groups from the cloud. You can push a policy to your endpoints that explicitly dictates who is allowed to be in the local administrators group.
So you can configure the policy to completely overwrite the local group.
Yes, ensuring that only the Untra global administrators and a specific group of desktop support technicians are present.
So if the help desk manually added that developer 3 years ago, the moment the Intune policy applies, it strips the developer out of the group because they aren't on the approved cloud list.
Yes, it forces the local reality to mirror your centralized intent.
Okay, this is a crucial conceptual distinction, so I want to summarize it clearly for anyone trying to build this mental model.
Go for it.
LAPS controls the password for the single built-in local admin account. It is the mechanism that prevents lateral movement by randomizing the master key. Local group membership management controls which users are granted local admin rights. It prevents privilege drift by strictly managing the VIP guest list.
That is a perfect summary.
They sound similar, they both deal with local administration, but they solve two entirely different operational problems.
You need both LAPS and local group management to truly lock down the physical endpoint.
This has been an incredible journey so far. We've configured identity policies, we're continuously evaluating device compliance, we've deployed seamless VPN access, and we've locked down local privileges to prevent lateral movement.
We've done a lot.
From an architectural standpoint, we have built an impenetrable fortress. But here is the reality of IT. I could configure all of this flawlessly on Friday, go home for the weekend, and come back on Monday to a total catastrophe.
It happens more often than you'd think.
How do we actually know any of this is working in the real world?
And that leads us to our final layer, operational visibility, generating inventory and reporting. The biggest conceptual trap in endpoint management is believing that deployment is the finish line.
Pushing a configuration profile in a portal does not mean the physical devices in the real world successfully applied it.
Exactly. Deployment is merely the starting line.
We need feedback, we need telemetry. Let's look at the built-in reporting capabilities in Intune. When an administrator opens those dashboards, what operational data are they looking for?
They're looking for the delta between intended state and actual state. You have hardware inventory OS versions, disk space, active primary users. But the most critical operational views are the compliance reports.
The aggregate visualizations.
Right. You see how many devices are compliant, how many are non-compliant, how many are in a grace period, and how many have simply stopped communicating with the service entirely.
Let me throw a real-world panic scenario at you. An administrator logs into the Intune console on a Tuesday morning. Yesterday, the compliance rate was 98%. Today, there is a massive red spike on the dashboard, and 45% of the entire corporate fleet is suddenly marked as non-compliant.
That'll wake you up.
The immediate instinct is that the network is under attack.
Mhm.
What does that data actually tell them?
While panic is a natural reaction, the data is there to guide a rational investigation. A sudden, massive spike in noncompliance rarely indicates a coordinated cyber attack or a spontaneous failure of hardware across thousands of machines.
It almost always points to a systemic administrative change,
So someone broke it.
or a policy worked exactly as designed, but unexpectedly.
The first step is to drill down into the specific compliance policy that is failing. Did another administrator update the baseline policy overnight to require an OS patch that hasn't finished deploying via Windows Update?
Oh, right. If so, the system is correctly identifying that half the fleet is missing the patch.
The policy is working too well. It's aggressively flagging devices based on a new rule.
Exactly. Or perhaps a new security software was deployed that conflicts with Microsoft Defender, causing Defender's service to crash. The compliance policy sees Defender as offline and flags the device.
The reports tell you exactly which check failed.
It shifts the administrator from panic to remediation. Do we need to pause the compliance policy? Do we need to send an urgent communication to users to reboot their machines to apply a patch? Reporting turns configuration into active management.
But let's scale this up. Clicking through web portals and drilling down into charts works great if you are managing 500 devices. What if I am architecting a solution for a global enterprise?
Like 100,000 devices across 40 countries.
Exactly. I cannot employ an army of analysts to sit and click through Intune dashboards all day looking for trends. We need to move beyond the portal.
This is where the documentation emphasizes Microsoft Graph.
Mm-hmm.
What is Graph conceptually, and why is it the answer to enterprise scale?
Conceptually, you can think of Microsoft Graph as the central nervous system of the entire Microsoft 365 ecosystem. Intune, Entra ID, Exchange, Teams, these are all individual organs or limbs.
Graph is the brain and the spinal cord that connects them all.
Technically, it is a unified REST API and application programming interface.
For those who might not be deep into development, an API is essentially a standardized way for different software programs to talk to each other without needing a human to click a mouse.
Precisely. Instead of an administrator opening a web browser, navigating to the Intune portal, and clicking Export to CSV to get a list of non-compliant devices, they can write a script, perhaps in PowerShell or Python, that sends a programmatic request directly to the Graph API.
The script essentially asks Graph, go query the Intune service, find every device in the London office that has failed the BitLocker encryption check in the last 72 hours, and return that data to me.
Yes, and Graph returns that data instantly, usually in a structured format like JSON, which the script can parse.
This allows large enterprises to pull massive amounts of custom telemetry data into their own specialized data lakes or security information and event management SIEM systems.
But reporting is only half of Graph's power. The true value at scale is automation.
Because if a script can read data via an API, it can probably write data and execute actions via the API.
Exactly. An enterprise can build a custom automation runbook. The system queries Graph every hour. If it detects that a device has been non-compliant for more than 7 days, the script automatically sends a warning email to the user and their manager via Exchange Online.
And if they still don't fix it?
If the device remains non-compliant for 14 days, the script automatically sends a command to Intune to move that device into a strict quarantine group, cutting off all network access.
Wow. It removes the human bottleneck entirely. The infrastructure manages itself based on the logic you define.
Now, the learning materials are careful to note that this isn't a coding deep dive. You don't necessarily need to memorize the exact JSON syntax to pass an exam or understand the architecture.
But understanding why Graph exists is essential. If you are operating at scale, Graph is the tool that transitions you from manual ClickOps to programmatic automated endpoint management.
Absolutely. The portal is for configuration and spot checking. Graph is for enterprise operations.
We have covered an immense amount of ground today. We set out to build a comprehensive mental model, and I think we've achieved it. Let's do a final synthesis of those 4 linked layers to cement these concepts.
Layer 1, strong user authentication. We are aggressively moving away from legacy passwords and symmetric risk.
We deploy Windows Hello for Business to leverage TPM-bound asymmetric cryptographic keys, making phishing credentials virtually impossible.
We implement robust self-service password reset with writeback to keep hybrid identities in sync.
And we utilize conditional access MFA, integrated with Entra ID protection to evaluate real-time signed-in risk and user compromise, stopping threat actors at the perimeter.
Layer 2. Secure organizational access. We are abandoning the clunky, user-dependent legacy VPN clients.
We deploy always-on VPN via Intune policies.
We leverage split tunneling coupled with local endpoint protection to balance performance and security, and we utilize device tunnels to ensure administrators maintain a persistent line of sight to the endpoint for patching and management, regardless of who is logged in.
Layer 3. Device trust enforcement. We recognize that a verified identity is useless on a compromised machine.
We deploy Intune compliance policies to act as the measuring tape, actively evaluating OS versions, encryption states, and defender risk scores.
We then wire that state into Entra Conditional Access, which acts as the enforcer, automatically blocking access to corporate data the moment a device falls out of baseline health.
And finally, Layer 4, operational security control, the internal safeguards.
We enforce the principle of least privilege using scoped role-based access control in Intune.
We neutralize the threat of lateral movement by deploying Windows LAPS to randomize and rotate the built-in local administrator passwords.
We prevent long-term privilege drift by actively managing local group memberships from the cloud.
And we maintain total operational visibility by actively monitoring compliance reports and scaling our automation capabilities using the Microsoft Graph API.
When you look at the material through this lens, it ceases to be a random collection of toggles and dashboards. It is a highly integrated, self-reinforcing ecosystem.
The identity controls protect the device health protects the network, and the operational controls protect the administrators from catastrophic lateral breaches.
That interconnected nature is what makes modern IT architecture so fascinating. I want to leave you with a final thought to ponder.
Oh, let's hear it.
The next time you sit down at your workstation, flip open the lid of your laptop and the camera flashes to recognize your face. Pause for just a second. Ask yourself, how many invisible, automated checks just fired in the background?
A whole lot of them.
In the milliseconds before you saw your desktop, the system evaluated your geographic location, verified your physical proximity via a hardware TPM, checked your credential status against dark web databases, scanned your local memory for malware, verified your disk encryption, and confirmed you weren't running as a local administrator.
It's pretty wild to think about.
You aren't just logging in anymore, you are passing through a highly orchestrated, incredibly intelligent security checkpoint. And as an endpoint administrator, you are the architect of that checkpoint.
That is exactly the mindset you need. And as a final wrap-up, this episode is a study aid, not official exam guidance. Always verify important details against the latest Microsoft documentation.
Thank you so much for joining us in the admin study room. Keep building those mental models, keep asking why and how, and we will see you next time.